Assalamu alaikum. Hope all of you are safe and you're staying indoors. Today I will be discussing bit reversal in FFT algorithms. If you remember the input sequence in DIT algorithm, that is decimation in time, the bit sequence was, I guess it was, if we say, let's assume n is equal to 8, then the bit sequence in that case, if you guys remember, if you're watching the classes, then it would be x of 0, the input sequence I'm talking about, x of 4, then x of 2, then x of 6, then x of 1, x of 5, x of 3, and x of 7. So this is my input sequence. This is for DIT, that's decimation in time. Now this there are total of 8 samples from 0 to 7. So I can represent these 8 samples, the index from 0 to 7. I can represent 0 to 7 as a 3-bit binary pattern. So if I can represent x of 0 as in 3-bit binary pattern as x of 0 0 0, right? Similarly, x of 4 can be represented as x of 1 0 0. X of 2 can be represented as x of 0 1 0. X of 6 as x of 1 1 0. X of 1 as x of 0 0 1. X of 5 as 1 0 1. Similarly, x of 3 as 0 1 1, and x of 7 as x of 1 1 1. This is a representation in binary pattern, right? This is a representation in binary pattern. So if I reverse this order, that is, if I take reverse of x of 0 0 0, similarly reverse of x of 1 0 0, it will be 0 0 1. So if I reverse them, so reversed order will be, x of, I can write it as x of 0 0 0, right? Then it will be x of 0 0 1, then x of 0 1 0, then x of 0 1 1, then x of 1 0 0, then x of 1 0 1, so then x of 1 1 0, and finally this extra one here, x of 1 1 1. So what I have done, I have written this binary, this was first written from left to right, so I reversed it. So basically I'm writing it from right to left. So say for example here it is x of 1 1 0, so if I go from right to left, it will be 0 1 1. That's the reverse order. So now if this is again in binary pattern, right? Binary pattern. So if I write it down in decimal pattern, it will be x of 0, this will be x of 1, right? So this will be x of 2, this is x of 3, this is x of 4, this is x of 5, this is x of 6, and this is x of 7. Now if you guys remember, then in case of decimation in time algorithm, what the input sequence was in this order, that's x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3, and x of 7, and the output sequence was in the order of capital. That was capital X of 0, x of 1, x of 2, x of 3, 4, 5, 6, 7. So what happens in this, we can conclude from this is that in case of the decimation in time algorithm, the output is in the normal order, that's from x of 0 to x of 7, whereas the input is in the bit reversed order. That's from x of 0, 4, 2, 6, 1, 5, 3 and 7. So bit reversal, so I can say input is in bit reversed order, right? Whereas in case of decimation frequency algorithm, that's when we decimate in frequency domain, then in that case what happens, that the input sequence is in normal order. It's from x of 0, 1, 2, 3, 4, 5, 6, whereas the output is in the bit reversed order. So I will write here, in case of and reverse is true in, reverse is true in decimation and frequency, fine. So this is it. This is bit reversal in case of FFT algorithms. Bit reversal happens in the input in case of DIT and in the output in case of the DIF. Fine. So let's stop here. Now I will be discussing the differences and similarities between the decimation frequency and decimation in time FFT algorithm. Fine. So the first similarity, the first difference. First, I will be discussing the differences. So the first differences. Fine. So the first difference is, let me underline it. Okay. So the first difference is that the one which we discussed just now, in DIT, the bit reversal fine, happens on input side, and in case of DIF, bit reversal happens on output side. Fine. So this is the first difference rather. Now if you guys remember, basically the FFT algorithms are based on the butterfly diagrams. So in case of DIF, the complex multiplication, there is a multiplication by the total factor, is done after we have done either the addition or subtraction, right? So after the butterfly, we do either multiplication or we do complex multiplication. Why is that called complex multiplication? Because WN total factor is basically e raised to something, so it becomes complex. So in case of e raised to minus j, so minus j is complex. So in case of DIF, the multiplication by the total factor is after the addition or subtraction. Like here, if I draw it here, if I draw it for 2-point DFT, so it's like this, then like this. Here we have addition, here we have addition. So excuse, then multiplication by total factor is here. That's after addition, multiplication by total factor is done, right? So in case of DIF, multiplication by total factor is after this summation here, right? After addition, or I can say subtraction. Fine. And in case of DIT, bits before addition or subtraction. Okay. So these are the differences. Now coming to the similarities. Number one would be number of butterfly computations. Additions, subtractions, and complex multiplications is same. So whether I'm going for DIT algorithm or whether I'm going for decimation DIF algorithm, the computational complexity remains the same. Why? Because number of butterfly computations, additions, subtractions, and complex multiplications is same. And second thing is both algos need, okay, they need it, they need bit reversal at some point, right? So this is it. This is the similarities and differences between the decimation frequency algorithm and the decimation time algorithm. Okay guys, so I will be discussing the computation of how we compute the inverse DFT using FFT algorithm. Now the IDFT of any IDFT, the general formula for IDFT of any n point sequence, you know, the formula can be written as, it can be written as x of n is equivalent to 1 by n summation k running from 0 to n minus 1 x of capital X of k e raised power minus j 2 pi nk by capital N, right? Or I can write it as 1 by n summation k running from 0 to n minus 1 x of k. In terms of total factor, it will become wn minus nk, right? Okay. So if I take a complex conjugate of the above equation, I will taking complex conjugate of above equation, then I can write x conjugate n will be equivalent to 1 by n summation k running from 0 to n minus 1 x of k. We'll take this one, wn minus nk whole conjugate, fine. Okay. So this will be equivalent to 1 by n is constant, so I can write it outside. 1 by n summation k running from 0 to n minus 1, so this becomes x conjugate k. So the conjugate of wn minus nk is Wn is basically a complex term, so we are taking complex conjugate. So e raised power, this is basically e raised power minus j 2 pi by n, right? So I can write e raised power plus j pi. So this becomes Wn plus nk. I can write Wn nk. Fine. So I'll scroll down. So this becomes equivalent to 1 by n. 1 by n summation 1 by n summation k running from 0 to n minus 1 x conjugate k Wn nk. Wn nk conjugate Wn minus nk is conjugate is Wn nk, right? So if this is x conjugate n, fine. So if I take its conjugate again, so I'll get x conjugate n whole conjugate, fine. So basically what I am doing, I am taking complex conjugate, and so this will be equivalent to x conjugate n whole conjugate equivalent to 1 by n summation k running from 0 to n minus 1, fine, x conjugate k Wn nk, this will be conjugate, fine. So this is basically equivalent to x of n. So x of n will be equivalent to 1 by n summation k running from 0 to n minus 1 x conjugate k Wn nk whole conjugate, fine. So let me go to the next page. Basically what I had to find x of n. So x of n, so using FFT algorithm. So what we have done, how we have calculated the x of n is, first, as a first step, I will take complex conjugate of x of k, right? So basically I will be getting x conjugate we will be getting x conjugate k, fine. So next step is that if we look at this formula, right, the one inside this conjugate, so it's x conjugate k Wn nk. So this and summation k running from 0 to n minus 1. So this is basically DFT of x conjugate k, fine. So the one inside these brackets, these square brackets, is summation k running from 0 to n minus 1 x conjugate k Wn nk. So this is nothing but DFT of x conjugate k. So second step will be compute, this is how many samples, n point DFT of x conjugate k, right? So you can use any formula using it can be radix 2, radix 4, whatever you wish to do, right? Radix 2 FFT, it can be decimation in frequency, it can be decimation in time. So so I have obtained this summation k. The second step, in using second step, I have obtained summation k running from 0 to n minus 1 x conjugate k Wn nk, and I am using FFT algorithm. So next step is to find the conjugate of this term. So next step will be take complex conjugate of sequence obtained by FFT, which we obtained in step number 2. Let me go down. The last step is division by n. So I'll write divide the sequence by n, capital N. Fine. So this is it, and the resultant sequence will be, so it means I have obtained sequence x of n. So the resultant sequence is x of n. Fine. So I'll be writing down a small exercise which you will do at home, and then you will share me the answers on the WhatsApp group. So you will obtain IDFT of, this is 8-point IDFT of x of k equivalent to 0 plus 3j 1 2 5 0 6 1 4 plus 3j using FFT. You will be using decimation and frequency. So you have to obtain 8-point IDFT of x of k, which is equivalent to 0 plus 3j 1 2 5 0 1 4 plus 3j using FFT algorithm, decimation, frequency. Fine. So this you will do at your home, and then you will jot down the answers on a piece of paper, and then you will take a photograph of that and then share your answers on the you will WhatsApp me not on your WhatsApp group, but you will WhatsApp me the answers. Fine. Okay, so I'll stop here. This is your lecture 4.